Hello, my name is Rafael Martins, and this is my progress report number 2 for the Applied Research Project course at Douglas College. I am developing an investment portfolio management application called InvestWise. The goal of InvestWise is to assist users in managing and analyzing their stock investments while providing predictive price insights using machine learning. The application is built with the MERN stack using MongoDB, Express, React, and Node.js for the core functionality. Additionally, I've integrated a Python-based machine learning component which runs on a Flask API to enhance the app's predictive capabilities. One of the standout features of InvestWise is the use of sentiment analysis scores from financial news combined with historical stock prices and other market indicators to help predict future stock price movements. Now, I'll cover the progress made on my project since the midterm report. My focus was primarily on the machine learning component, where I implemented several enhancements to improve the model's predictive capabilities. Additionally, I made updates to the web app to provide users with more informative and visually engaging charts. To enhance the machine learning model, I implemented a Python component that was responsible for fetching sentiment analysis data and historical stock price data from the AlphaVantage API. This API provides new sentiment scores and price data for the past 3 years. However, one of the key challenges I faced was managing the API usage limits. Initially, I used the free tier of the Tingle API for basic price data. However, due to the extensive data requirements for model training, I upgraded to a premium plan on AlphaVantage, which allows me up to 75 API requests per minute without daily limits. Even with this increased limit, I had to carefully adjust the data fetching script to avoid exceeding the API quota while processing thousands of data points. After fetching the sentiment and price data, I explored the datasets to ensure consistency, aligned the timestamps between them, and merged the datasets. Since there could be multiple news articles per day with different sentiment scores, I aggregated the sentiment data by day and used the average sentiment scores. This merged dataset was then saved as a CSV file for training the machine learning model. The stocks selected for the model training were carefully chosen from popular and frequently traded stocks, including those in the S&P 500 index. This decision was made to ensure a diverse and well-represented dataset across multiple industry sectors. The chosen stocks not only have ample news coverage, but they also have higher volatility, which is beneficial for model training. From this point, the project entered an iterative cycle of model training, evaluation, and refinement. I conducted extensive research on alternative approaches to enhance the model's performance, and this involved feature engineering, dealing with imbalanced data, and fine-tuning the calculation of the target variable. To capture more meaningful trends, I incorporated additional technical indicators derived from the historical price data. For example, I calculated indicators like relative strength index, which measures the speed and magnitude in which the price changes, the average true range, measuring volatility by checking the range between high and low prices, and Bollinger Bands, another volatility indicator with 3 main components, being the middle band representing a simple moving average of the price, an upper band representing potential price resistance, and a lower band representing potential price support. These indicators help capture patterns and volatility that basic sentiment and price data may miss. Additionally, extra sentiment features were engineered, such as the minimum, maximum, and standard deviation of sentiment scores. For the final model, I defined a target variable using a threshold of 1.8% to classify the price movement. If the stock price increased or decreased by at least 1.8%, it was labeled as significant movement. Otherwise, it would be labeled as no movement. This threshold helped to reduce noise and capture more meaningful fluctuations in the stock price. However, this introduced a new challenge, which is class imbalance. To address this, I applied a hybrid resampling technique called small team, which combines oversampling and undersampling to balance the dataset. As we can see in the screenshots, The class distribution was significantly imbalanced before applying the resampling technique, but small team handled it, as we can see in the final class distribution. To get to the final model, I experimented with several machine learning algorithms, including XGBoost, LightGBM, CatBoost, Random Forest, Logistic Regression, and Support Vector Machine. After evaluating the models, XGBoost demonstrated the best performance. The classification report of each of these models is displayed in the screenshots, showing metrics such as accuracy, precision, recall, and F1 score. I also analyzed the feature importance using the XGBoost model, but found that removing less important features led to a decrease in evaluation metrics, which is also shown in the screenshots. Therefore, the final model includes all 26 features. Once the model was finalized, I created an API route within the Python component to handle prediction requests. This route receives information about a stock, processes it, and then returns the predicted price movement. The web app communicates with this Flask API endpoint to retrieve the predicted values and display them to the user. The diagram on the left represents this process, and the snippet on the right shows a test call performed on Postman. Now, I'll demonstrate the prediction capabilities of the machine learning model integrated into the InvestWise application. We'll test 3 different scenarios using Postman to make API requests: a strong increase in stock price, a decrease, and another scenario where there is no significant movement. In this first example, as you can see, we'll test a case where the model predicts a decrease in stock price. The input data includes negative sentiment scores, bearish technical indicators, and a drop in the adjusted close price. Next, we'll test a case where the model predicts an increase in the stock price. The input data includes positive sentiment scores, bullish technical indicators, and an upward price trend. And finally, let's see a case where the model predicts no significant movement in stock price. The input data for this scenario shows mixed sentiment and stable price indicators with minimal changes in stock price. Now, putting everything together, let's open the application and see how the web app communicates with the Python component to get the predicted price movements. Here we can see that for each stock, the web app is sending the request to the Flask API to get the prediction of the price movement. And in addition to the machine learning component that we've been talking about so far, I also made some enhancements to the web app's user interface. Here I added a donut chart to visually represent the distribution of stocks in the user's portfolio, and an area chart, which I'm still working on, to show the evolution of the total invested amount versus the total wealth. These visualizations provide users with a clear overview of their investment performance. To conclude this presentation, I want to take a moment to highlight the part of my project that I am most proud of, which has been the machine learning model development process, which I found both the most challenging and the most rewarding aspect of the entire project so far. Working with real-world financial data presented unique challenges, from inconsistent data formats to missing values and timestamp alignment. I had to deal with a variety of issues that are common when working with external data sources. This experience was invaluable because it taught me how to navigate these challenges effectively, and I learned the importance of a detailed data exploration and rigorous pre-processing to ensure the model was trained on a high-quality data and a reliable data. Another key learning opportunity came from the feature engineering phase. While researching and implementing technical indicators such as RSI, ATR, and Bollinger Bands, I not only deepened my understanding of financial analytics, but I also learned how to translate these indicators into meaningful features for machine learning. This experience pushed me to go beyond the basics of model development and really think about how to extract valuable insights from raw data. And finally, the process of optimizing the model through hyperparameter tuning and experimenting with different algorithms was a significant learning curve for me. I explored various approaches with different machine learning algorithms, comparing their performance and refining the model through multiple iterations. The challenge of balancing the model's complexity with its ability to generalize well taught me a lot about the iterative nature of machine learning projects and the importance of constant evaluation and refinement. Overall, the experience of building this machine learning component has been incredibly educational. I have gained a deep understanding of the end-to-end data analysis pipeline, from data extraction and feature engineering to model training and evaluation. This process has not only strengthened my technical skills, but also enhanced my understanding of financial data analysis. It has been a great learning opportunity, and I am excited about the potential of the model to provide meaningful insights in the InvestWise app. Thank you.